Hello everyone, my name is Sarah Berry and welcome to my presentation on Physics Lab 1. In this lab, I studied the motion of an object at constant velocity and compared a real experiment to a computer model. Over the next few minutes, I'll walk you through the purpose, procedure, data, and conclusions. Here's an overview of the presentation. I'll start with the introduction, then move into Newton's second law. After that, I'll describe the procedure, summarize the data and code, and then share the comparisons, discussions, and final conclusions. The main goal of this experiment was to observe an object moving at constant velocity, meaning its speed and direction don't change, and then compare that real-world motion to a computational model. This experiment highlights Newton's second law, also called the momentum principle. In simple terms, when the net force on an object is zero, its velocity doesn't change. That's exactly what we set out to test this lab. Newton's second law is fundamental in physics. It tells us that force equals the change in momentum over the change in time. Since momentum is mass times velocity, any change in velocity means a change in momentum. If there's no net force, then momentum stays the same, and velocity stays the same. This law is what connects the data we measured in Tracker to the simulation I built in GlowScript. The procedure began by recording a soccer ball rolling at a roughly constant velocity. I then used Tracker software to mark the center of mass, add a calibration stick for scale, and set up coordinate axes. After collecting experimental data, I built a computational model in GlowScript. There, I programmed the ball to move with the same initial conditions and no net force. Finally, I compared the graphs from the video and the simulation to see how closely they matched. In the experimental setup, the soccer ball was the system and the ground was considered part of the surroundings. The video ran from 0 to about 1.5 seconds. The ball started at the origin with an initial velocity of about 0.08 meters per second in the positive x direction. These measurements set the baseline for comparing to the computer model. Here's the graph, and here is more data. Watching the video, the ball's motion appeared smooth and steady. There wasn't a noticeable slowdown, which means outside forces, like friction, had only a small effect. This supported the assumption that the ball was moving at a constant velocity, even in a real-world setting. In GlowScript, I defined the ball's initial position as the origin and set its velocity to negative 5.97 meters per second in the x direction. The time loop ran until just over 2 seconds. Importantly, I set the net force to 0, so the velocity stayed constant. The position was updated step by step using the velocity, and the velocity itself remained unchanged, which perfectly represents constant motion. The model produced a position time graph that was a straight line with a positive slope. That slope shows the ball moving steadily forward. Since the line wasn't curved, we know there was no acceleration, and therefore no net force was acting. This matched the expected outcome. When comparing the graphs from Tracker and GlowScript, both showed straight lines with positive slopes, confirming constant velocity of motion. The main difference was in the starting position. The computational model began slightly higher than the experimental data. This reflects small differences in setup and measurement, but not in the overall trend. Like any experiment, this one had potential sources of error. Friction, although small, could have affected the real ball. Tracker also is not perfect. Marking the ball's position frame by frame can lead to small errors in distance and velocity. These two factors likely explain why the experimental and computational data weren't identical. In the actual setup, the ball moved from left to right, which we treated as the positive x direction, but if the coordinate axes had been flipped, the same motion would appear in the negative direction, and the slope of the graph would be negative. This doesn't change the physics, but it shows why being clear about axes is important. So what does that tell us? Even though we can't count the exact number of small forces acting on the ball, the fact that it moved with constant velocity means the net force was 0. In other words, any pushes or pulls balanced out. No accelerations means no unbalanced forces. To conclude, this experiment confirmed Newton's second law in a clear way. The soccer ball kept its speed and direction, meaning no unbalanced forces acting on it. Both the experimental data and the computational model supported this. Together, they show how physics theory and real-world evidence work hand in hand.